Hello, welcome to my presentation about wastewater treatment, specifically how ferric chloride is used for coagulation. The history of wastewater treatment, as far as many people know, can go back at least 1,000 years to when outhouses were very popular, even for the Vikings in their backyard, so that they don't have to poop in their house or poop in the dirt or have their feces smelling up everything and being filthy. So it wasn't actually until around the 1800s where in the big cities there started to be a lot of waste in the streets and everything was really filthy. So whenever to control diseases, the cities actually implemented buried sewers and sand filtration systems for the water, which some sand filtration systems are still used today. Now, wastewater can include many different things. It can include road water runoff, animal defecation from farm use. It could also include chemical waste from industrial manufacturers. But usually, most people nowadays know not to flush chemicals down the drain, as professors in chemistry 405 has taught us. But wastewater can also include um, raw sewage that our septic companies pump out of our septic tank. You can't dump chemicals down the drain for a lot of the same reasons that we can't dump our raw sewage into our lakes and streams. Just bad things would happen. It would ruin not only our ecosystems around us, but it would potentially cause harm to our everyday lives. It would make our lakes, like in this photo, Lake Erie, it would make it a disgusting green color. It would make my lake across the street have a blue-green algae, which it does have. I'm not sure if it's from raw sewage or whatever, but there's a sign across the street from my house. It says, "Don't go in the water. Don't let your pets drink it. It's toxic. It's bad for you." Bad things happen. Eutrophication would happen, eutrophication is when algae blooms happen, which is algae growing so quickly, consuming so much oxygen from the reproduction of the algae that it kills off other wildlife and other plant life because the ecosystem isn't made to sustain that much living life. And so never is it okay to dump your camper sewage into the lake. Never is it okay to
Raw sewage going into our ecosystem is happening all over the world. There's still places in Canada up until this day that is dumping their sewage into the lakes and oceans that is accompanying the United States. Canada is right next to us and they're doing it. We have to treat wastewater before we send it back into the environment of which it may have came. This can be done in many different ways through a wastewater treatment facility. As my Uncle Phil said, who is a wastewater foreman, wastewater treatment plants are like a snowflake. They have many of the same designs and same concepts, but each one is unique in their own way. But generally there are 4 steps. There's pre-treatment, primary clarification, secondary treatment, and the tertiary clarification. And so, generally, in between the pre-treatment and primary clarifiers, there is a tubing with mixers that mix in chemicals into the flow of water so that by the time the water reaches the primary clarifiers, the coagulation has already occurred. What coagulation is coagulation is when small particles react with an aqueous solution to form solid clumps of material. Many different chemicals can be used to do this. Some are more expensive than others, some are more corrosive and dangerous than others, but one of the most common chemicals used to this day and a good option is ferric chloride.
Ferric chloride is known as a metal salt. It's an aqueous solution, which means that it is liquid. It is very corrosive and requires special machinery, special pumps to mix in the chemical with the wastewater, because if normal pumps and normal machinery is used, then it would be corroded and break. The machines would break and clog up and stop working very easily. Yeah, ferric chloride is a unique chemical because you can't just make it how you would expect. You can't just make it by mixing iron and chlorine, even though the formula for ferric chloride is FeCl3, which means that it has an iron and 3 chlorine. But you have to oxidize ferrous chloride, which ferrous chloride is FeCl2. And what oxidizing is when you remove an electron. And so ferrous chloride is iron with chlorine when the iron has a +2 charge. So if you oxidize it, which means remove an electron, it gives the iron a +3 charge, which is the charge of ferric in ferric chloride. There are alternatives to using ferric chloride for wastewater treatment. One alternative that I found noteworthy is aluminum sulfate. It is less corrosive and it costs less in the upfront cost of building a facility because you don't need quite as expensive of machinery. You still need good machinery that you want to last, but it is also more expensive in the long run because it is a more expensive chemical to produce. But both chemicals do the same job. They're both metal salts used for coagulation. The coagulation is done in the formula shown right here. The ferric chloride reacts with phosphate, which is an excess nutrient. I'm going to be repetitive on that. An excess nutrient of organic matter. Nitrogen and phosphorus are two very common examples. There are strict regulations for these contaminants that is allowed in the effluent stream, the outflow of water coming out of a wastewater treatment facility. So these two contaminants are things that my uncle, the foreman at the Pease Air Base, is constantly looking for. If it goes above a certain level in concentration of parts per million, then he's always on call. If it goes above a certain level, then he has to go in and figure out why the pumps aren't working correctly or why the chemicals aren't doing their job.
If what I'm trying to explain to you is still a little muddy, let me put it this way. The majority of excess nutrients that need to be removed from wastewater to prevent catastrophic environmental disasters is removed with coagulation, which is when two aqueous solutions, kind of like with precipitation, it's when two aqueous solutions react with each other to form a solid. These aqueous solutions are wastewater and a chemical, usually metal salt, such as ferric chloride. The wastewater is water containing excess nutrients such as phosphorus. So the water and phosphorus creates a hydrogen phosphate. And so when you mix ferric chloride and hydrogen phosphate, you get ferric phosphate, which is a solid. This solid is easily removed in the primary clarification step, which I'll explain to you on the next slide. The chemicals are usually added into the stream early on in the wastewater treatment process so that the coagulation has time to occur before it reaches the primary clarifier. So after the grit building, the chemicals are added, solids are started to form, and then when the water gets to the primary clarifier is a big circular pool with a drain in the bottom, and the pool is getting mixed at the rate that gravity pulls these solids down to the bottom of the pool, pulls it through a drain in the bottom. And so when all the solids are settled out and all the cleaner water is going to the top of the water because it's lighter, the water spills over the top edge and it goes over on its way to the secondary clarifiers, and then the secondary clarifiers grow bacteria that consumes more of the excess nutrients. And then after that, the water goes over to the tertiary treatment, which is when chlorination or ultraviolet radiation kills off the remainder of the bacteria so that it can't reproduce and is no longer harmful. And then the water can finally be given back to the environment. In summary, there are many different types of wastewater treatment facilities around the world, but they all need some type of chemistry. They usually rely on some type of metal salt for the process of coagulation to limit the contaminants that would otherwise be very hard to remove from wastewater, so that devastation does not happen in our ecosystems around us. So there's actually so much future work involved in the wastewater treatment world. I actually kind of want to get a job in it because I could help my own hometown solve my algebra problem, but I could also go work in the Portsmouth facility and help engineer a new solution, a cheaper alternative to ferric chloride, the pumping systems and everything else needed to produce clean water. We need to make the process cheaper so that we can spread the technologies around the world. Places like Canada, places in foreign countries that don't have the funds to produce a $100 million facility like Portsmouth did. We need to get everyone involved and stop ruining our ecosystem more than we already have.